I'm Nazar Karpyuk from Lviv Polytechnic National University, and the theme of my presentation is Streamlined Near Real-Time Image Processing with Apache Kafka. I will start with obvious statement that in the era of big data, the ability to process a large amount of information in real time has become very crucial for application dealing with high velocity data streams. For example, like image processing, the traditional batch approach that is mostly used right now is simply falls short. This is where an event streaming emerges as some powerful method enabling the continuous transformation of images, the analysis of data, and in the way that as it arrives to the system. And at the forefront of this so-called revolution stands in Apache Kafka. This is an open source distributed platform, and by leveraging its robust architecture and capabilities, the near real-time image processing becomes a reality by unlocking a capability of some innovative applications across different domains. Now let's talk a little bit about Apache Kafka itself. Kafka operates on a distributed architecture that consists of some several key components that orchestrate the flow of data inside the system. Those are producers that act like some kind of data injectors by continuously sending streams of events, in this case, images and part of images to the system. These events then publish to the topics some sort of logical challenge that categorize and group related data. Then brokers receive and manage events, replicate them across the cluster for high availability and fault tolerance. And in the end, the consumers in turn subscribe to the specific topics, pull and process the events as they arrive. And all in all, this producer consumer architecture ensures scalability and flexibility that allows kind of independent scaling of each component based on the processing needs. For example, for producers, consumers, or a Kafka cluster itself. Now, let's go back to our system and quickly review the image preparation part. This part we can imagine like some kind of data intake pipeline that's responsible for retrieving images from designated storage locations. As you can see in a diagram, it could be some picture storage as well as a video or even a stream from surveillance camera, for example. Though, as you can see, videos and video streams will first need to be converted to a sequence of images by utilizing some framework or library. In this case, in my project, it was one from OpenCV package, while next, by utilizing a pillow library from Python, images transform from RGB or RGBA color model into a binary arrays that represent pixel data in some compact and computability efficient format. Then subsequently, these serialized images, or let's say arrays, are published as messages onto the Kafka cluster. As for the image processing part itself, this component is a part of a consumer side of systems and comprises a set of Python applications that designed to consume and process the image messages acquired from Kafka cluster. And by using an appropriate image processing library, these applications can extract meaningful information from the received data or perform tasks such as resizing, object recognition, or even some kind of image classification. So, as it has probably become clear by now, by the correct and most importantly efficient functioning of the system, it is crucial to properly configure it, choose the right number of brokers and topics, and don't forget about producers and consumers, since they for sure need some proper connection to the system. Fortunately, most of the settings are made by simply by changing the parameters in the related system configuration files. And in addition to the settings, the development of the system itself was not without problems and bottlenecks. For example, receiving images, converting, let's say, images to data arrays for further processing was initially challenging, but solved with Pillow library from Python. However, handling a large amount of these pictures required a further optimization. Secondly, the system can process both images and videos quickly. It's a modular design that allows easily integrate various image processing tasks. It also can handle an increasing data loads due to its distributed architecture. However, complex tasks on high-resolution images can introduce some delays. So the choice of image processing libraries can also affect the performance. While some libraries offer many functionalities, they may be slower and than more specialized ones. And again, complex image processing, especially on high resolution images, can slow down the system due to obvious hardware limitations. So powerful CPUs or GPUs are obviously needed for demanding tasks. Now let's check the performance plots. Intuitively understandable that some increasing in the number of brokers in Kafka cluster leads to improved throughput for both image sizes, for small and big. This is because the load of handling incoming messages is distributed across more nodes that enables some parallel processing and reducing the bottlenecks. However, as you can see on the left plot, the improvement stops after a certain point due to the overhead associated with the managing of additional brokers that we added in the cluster. And while increasing the log size, the right picture, mm, initially it has a minimal impact on the throughput, but exceeding a certain threshold, in this case about 50 megabytes, is that introduce some log management overheads that negatively affect the performance. So this emphasizes the need to implementing an efficient logging practices, the strategies to avoid the compromising system responsiveness. And as for final conclusion, the developed near real-time image processing system that utilizes Apache Kafka demonstrated its potential for various applications, and the model architecture facilitated diverse image processing tasks while ensuring scalability and fault tolerance. However, system performance is highly influenced by several factors, including image resolutions that we are using, process complexity, hardware limitations, and network latency. Careful consideration of these factors are very crucial for achieving a needed near real-time performance in practical applications. And further work could explore integration with specialized hardwares like GPUs, or even leverage some cloud-based infrastructure for scalability. So thank you for your attention. That's all from me now. And I would be more than happy to answer your questions.
Thank you, dear Nazar. Questions, please, dear colleagues. I have one small question about where can your results be used, in which areas we...
Okay. I understand the question. Well, as you can see, Sergey was the first presenter, showed us some pictures of X-rays of the tooth in some medical center. So, as I say, the lens, let's say a pixel length and height of a picture highly affects the performance. So this kind of pictures where it's standardized resolution is perfectly fit for this application, for this system. And it's better to use the system in some way where where it was there was utilized some stream processed framework earlier, so it was easier to set up, because this system works not so well like some machine learning. But if the corporation, let's say, already utilize some Apache Kafka or Apache Flink, it's I say it would be better to implement this image processing than some develop a new one.
Thank you, Nazar. More questions, please, dear colleagues? No more questions. Thank you.